So in the last section, we looked at the Paxos algorithm, and here we will look at the implementation of the algorithm and trace some of its executions. We did in the live lecture look at some of this material, but it was done in a hurry, so I'm re-recording. So remember, Paxos is a complicated algorithm. It's got 3 phases, and these 3 phases are extensions of something simpler we saw in a 2-phase algorithm, which could be centralized or not centralized. And what I will do is, rather than talk about the implementation from scratch, instead look at how it modifies what we know already from the centralized consensus mechanism, which in turn is a subclass of the synchronous consensus mechanism, and the top level being the asynchronous consensus mechanism. So on the left, you see the operations that these consensus mechanisms make on each other in a distributed fashion. So these are the distributed operations, and they're internal. They're not seen by the user, by the application programmer using the consensus mechanism. On the right, you see the operations that the application makes, and the 2 main operations are propose and add consensus listener, where the listener is invoked whenever a new consensus value is achieved. Okay, and the operations on the right are not exhaustive. There are many other operations, some of which allow you to customize, and we will look at some of this customization later. And of course, I won't I show you the complete code, just the code outline. Okay. So since Paxos subsumes, at least our implementation subsumes the previous implementations, we will define a helper function that determines whether we will use the new functionality or use the inherited functionality. Okay. So we don't want to use Paxos if we don't care about atomicity, if we can allow concurrent operations to execute in any order. And if this ordering is done by a centralized process, then again, we don't need Paxos. Okay. Let's start with the basic operation of propose. Remember, propose it can be either remote or local. And if it's remote, we don't have to worry about it in Paxos because we're looking at the basic Paxos algorithm, which has no centralization. So if it's local, then again, we don't really have to use Paxos. If it's not atomic, then we can just call the superclass method. Otherwise, we start the Paxos algorithm. Okay? And if you remember, the Paxos algorithm starts, or the Paxos propose starts with the prepare phase. So the prepare phase just simply records the fact that we have prepared and sends the prepare request to all the acceptors. Okay, so let's see what happens at the acceptor end. So this is the method that's called in the acceptor when the prepare request is sent to it, and it takes a proposal number as Lamport's algorithm requires, and also a proposal value, which is something I've added, and we'll see a little later why. So what this method is supposed to do, if you remember, is both do a get and a set. And this part, so this is what is being shown in this purple box here. And this part of the code addresses only the get part. Okay? And the get part also involves 2 things: calculating what should be sent back, and actually doing the send. And this code just calculates. Okay? And what we calculate, we have some choice in. Okay? If we have accepted something before, then we send that accepted value along with this proposal number. And we haven't accepted anything, then we can send empty values for these 2 items, or we can send the last seen proposal number. Okay? And we will send the last seen proposal number to make the algorithm converge faster. Okay? So we first assume that we have had a successful accepted operation executed on this node. Okay, and that's what this variable holds, that value. And if it's not -1, then indeed that has been a success, that we have a successful accept, in which case we look at the accepted state associated with that last successful accept. Okay. Otherwise, we make the proposal number be the last proposal we have seen. Okay. So what we send to this helper function is either a prepared number or an accepted proposal number. And whether it's prepared or accepted is decided by this logic here on whether we have an earlier acceptance or not. And we send the accepted state, the new proposal number, the new proposal, and also a check for whether the prepare request is a successful one or not. Okay, and it's successful or not depending on whether we have a concurrency problem or we have some other problem. Okay, so let's go and see what this check prepare request does. The check prepare request, like I said, checks if we have a concurrency problem. And if there is such a problem, we send back a concurrency conflict. Or as in our previous code, it checks with a local vetoer to see if the local site can actually accept the value. Okay, this is something we did in the previous algorithms. And this is something not in Lamport's algorithm, but I think it allows for that. And we have to check the vetoer some point, either in the accept phase or the prepare phase. And we might as well check it as quickly as possible. So that's what I'm saying here. State-based rejection should be done as early as possible. And just to remind you, the reasons why we may not accept something locally is because we may not have space, there may be something corrupted in our disk, there may be so many other problems. So as we see in this Google Drive example, that we might not have access, for instance. So there may be some corruption. So that's what we're doing here. And remember, the vetoer is a local vetoer. So if any one of our vetoers says no, we send back a response saying that there's a problem. Okay, that doesn't mean that our response will veto everybody else's response to the prepare request. Okay, when talking about majority, we see whether we have a majority acceptance or not whether we have a single site vetoing or not. Okay, so that's state-based rejection. And this code shows you how a concurrency conflict is determined. This is pretty much what we saw earlier in the algorithm. That if the proposal number is earlier than what we have seen before, then we have a concurrency conflict. Okay, so let's go back to this code. We have calculated what we need to send using the help of check prepare request. Now we have to do the actual sending, and also you have to do the sending. That's being done here. And there are three alternatives here. Either we had no concurrency conflict and the state was okay, in which case we send back a successful prepare response and we record it before sending, or our feedback kind showed lack of success. We had a concurrency problem or the state was wrong, in which case we may or may not send back a response, and the process prepare rejection method determines whether we are going to send back a response or not. And in my implementation, by default, we do send back a response. Okay, that's customizable, but the customization by default allows it to be sent. There's a third, more subtle alternative, that we don't need to send back anything. That is too late. Okay, so it's possible to get an accept request from a site before we receive the prepare request from it. And if that is the case, then we return. Okay, and also because that can happen, the accept phase may have gone so far that the value is no longer pending at a site. Okay, we've received enough accepted notifications at a site to know whether the proposal is accepted or not, or rejected. Okay, so in either of these two cases, we don't send back a value. Okay, this is important because the processes rely on majorities rather than complete acceptance and preparation. Okay. So the next step is to see what happens when a prepared method is called in the proposal. Okay, so the proposer executed the prepare method in the acceptor, and the acceptor invokes a prepared method in the proposer. It can be invoked in the successful and the non-successful case, depending on whether we are sending back non-successes. So this prepared method handles both. And this is probably the most complicated part of the algorithm. We record the fact that we've got a prepared notification. That's just bookkeeping. And we may have already, we may no longer need this prepared response. Okay? If we get a majority of appropriate prepared responses, we start our accept phase. So this prepared response may arrive too late. Okay? And it may be too late in two ways. The prepare phase may be over, so we are now in the accept phase, in which case we don't have to do anything. Or the algorithm may have gone even further and the value is no longer pending. In either case, we return without doing anything else. Then we check if the feedback kind is concurrency conflict. And if it's concurrency conflict, we don't want, we'll abandon a proposal because a proposal is, there's another proposal with a higher number. So there's no point doing any more work. And we'll indicate the fact that our proposal is now no longer pending by putting a new proposal state here. Okay, that's a function of what feedback we got here, which is of course concurrency conflict. Otherwise, we want to go and process that request and see whether we've got enough requests to take some action. Okay, and this is just like what we did with the accept in the accept phase in the synchronous algorithm. We aggregated the accept responses to see whether we can take a further action. Okay, and here's the aggregation. We first check if we've got enough. We call this helper function to determine how many requests we've got so far and how many of them have been successful. So if we haven't had enough requests to make a decision, we get a null value here, in which case we just return and wait for another response. And if we have had enough, then we go and indicate the fact that our prepare phase is over. Now we have to decide whether we have to start the accept phase or not. So we go and look at how many agreeing prepared responses we got, the ones in which there were no conflict. And if there were enough, then we start the accept phase. Otherwise, we go and say that we didn't get enough prepared responses and change the proposal state. Okay, and it's no longer pending now. And when we start the accept phase, we have to decide what value to propose. Okay, and remember that if we have seen no accepted value so far, then we send our own value. Otherwise, we repropose the accepted value with the highest proposal number. Okay, that's what this code is doing. It's trying to determine whose state we are going to actually propose. The state associated with our proposal number, or the state associated with something we received in our prepare responses. And we look at the maximum accepted proposal number received in the prepared notifications. If that is not a valid value, then we use our proposal number for the proposal state. Otherwise, we use the maximum accepted proposal number. Okay? So that determines whether we repropose or propose a new value. And once we know what value we are proposing, we can start an accept phase. And the accept phase is pretty much like it was in a synchronous algorithm. Okay. There are a few differences though. In our synchronous algorithm, the accept request at the acceptor checked the vetoers. Okay. Now the vetoing check was done in the prepare phase. So if it's not Paxos, we go and check the vetoers, and by basically saying super.check accept request. Otherwise, we just have to go and check if there's a concurrency conflict or not. Okay, whether the proposal to be accepted is lower than something we've seen before. Okay, and so we call this helper function to determine if there's a conflict or not. And so there's no application-specific check in this phase under Paxos. Okay, the veto wasn't. So the accept concurrency control conflict condition is the same as the prepare concurrency control conflict. The proposal number is something that is lower than what we have seen before. So there's integration of both the prepare and accept phase in this aspect at least. And another aspect also there's integration, that when we record the received accept request, we update the same value as we update when we record the prepare request. Okay, so we update the last seen proposal number, which may be an accepted proposal number or a prepared proposal number. Okay. So there's a few more things we have to do differently in the accept phase, and they have to do with the architecture, with who gets what message. So in the synchronous accept phase that we saw earlier, that we are modifying right now, the node that sent the accept request is the one that gets the accept response. Okay, and then it goes and sends them to the learners. In Paxos, the accept response request is sent by the proposer, but the response is sent to the learners directly. And there is no need to go and send information to the learners from the proposer. So we have to make these two changes in our. Okay, so in what we see in the top method here is the superclass code that goes and when it learns about a new value, and this is executed in the proposer in the synchronous case, it goes and sends a learn notification to everybody else. Okay, so it does a local learn, and then it sends the learn notification to others. Now, each node will get the learn at the accepted response directly, so there is no need for the proposer to send a learn notification to others. So in our Paxos specific class, we check if we are Paxos or not. If we are not Paxos, we do whatever our superclass does. Otherwise, we do nothing. Okay, so learn values are not broadcast in basic Paxos. Okay, in the variation that reduces the number of learn requests, learn responses, there's a central learner that goes and sends a learned value. But in the basic Paxos, there can be multiple learners, all of which get responses directly. Okay. And this is the response, the code that decides who gets the responses to accept a request. And if it's not Paxos, do whatever the superclass does. Otherwise, we send the accepted notification directly to the learners so they can each invoke an algorithm to learn the majority value. Okay. Okay, so that was the implementation. And as we did with the previous implementations, we will exercise this implementation on various examples to illustrate how it works. And like the previous examples, we'll have two proposers, both trying to propose a value for the meaning of life. And this time we'll have only one non-proposer node, node 2, rather than two of them. Okay, so let's look at what Paxos algorithm properties I want to illustrate in each of in the first example. So remember, the proposer sends his proposal and value if majority of acceptors have not yet accepted any value. Okay, and each acceptor accepts a proposal if its proposal number is higher than what it has seen so far. So this is the simplest case, in that this is the case that's exercised when you first propose a value, and you have two nodes, and 1 and 3 will find no previous acceptance, and 1 will find no previous prepare. Okay, 3 will find a previous prepare, but its proposal number will be higher than 1's prepare, so its prepare phase will also succeed. Okay, so because its prepare phase succeeds, 1's accept phase is rejected, but 3's accept goes through. Okay, so that's what we should see. And how do we make sure that this sequence of events occurs? I've done this by setting breakpoints in two of the methods, start prepare phase and start accept phase, which are in the consensus mechanism. And by doing appropriate resumes in each of the processes 1 and 3, I can make 1 prepare be executed before 3 prepare, and then 1 accept and 3 accept. Okay, and this shows the log at node 1. Okay, so we know it's node 1 because the very first line says making proposal of 42, and node 1 makes the proposal of 42 and node 3 makes the proposal of 29. And the proposal number indicates the site ID. So this is the first proposal made at site 1, so its proposal number is 1.0001. And we see here, so let's see what we see. Okay, we see that the prepare is made for 1 and by 1 for the number 42 associated with proposal number 1.0001. And there's also another proposal made by a higher numbered proposal for a different value. Okay, so these two actions occur in this order. And because 3's action occurs after 1 has aggregated all the prepare responses, which you see between these two lines, 1 will go and send an accept. Okay, and it'll not only send the accept, it'll also receive its own request because it's also an acceptor. And but that also an accept request is received from node 3. Okay? But because node 3 had done a prepare before node 1 did an accept, you get all these concurrency conflicts and denials between the two lines. And you see one of these here. And you see the individual denial, and then you see an aggregate denial saying I have heard 2 denials, so that's overall denial. Actually, the very first concurrency conflict will cause it to abandon the proposal. Okay, and we achieve consensus not with the value 42, but with the value 29 that was proposed by the higher numbered proposal. Okay? And you see that after we have reached consensus, we get a few extra messages. And these are the messages from the nodes we didn't consider. We made our decisions as soon as we got majorities. Okay, so the fact that node 3 rejected node 1's proposal of 42 arrives later, and the fact that node 3 accepted its own proposal also arrives at node 1 after node 1 knows what the right value is. Okay, so if those two messages never arrived, those two they got lost, we would still reach consensus. Okay, so as long as the majority of nodes respond with answers, we will reach a consensus. Okay, so these are the late messages. Okay, so we've seen 2 of the properties. Let's go and construct an example that shows another property, that a prepare abandons proposal if it learns about a higher numbered proposal. So we'll find that 1 finds a higher numbered proposal in the prepare phase, not in the accept phase, in the prepare phase. And we just have to go in, we have to put breakpoints in the same 2 methods as I did earlier, but this time we resume in a different order so that 3 prepare goes before 1 prepare. And this log, if we look at it carefully, this is now shown from 3's point of view. So this is 3's log, and it receives, it sends a concurrency conflict message in its prepare phase to 1. And so we know there's a conflict, and so there's no accept there. Okay, here's the most interesting aspect of the algorithm, that a proposer with a higher proposal number might repropose the value that it learns about from a lower numbered proposal, and especially if it's a majority value. Okay, so that happen. 3 finds majority acceptances from 1 in prepare phase, so it will repropose 1's value in its accept phase. Okay. Again, we have the breakpoints at the same 2 methods, and we just resume them in different order to make sure that 1's accept goes through before 3's prepare starts. Okay, so everybody will go and tell 3 that they have accepted 1's value, and it will make a decision based on just 2 nodes. Okay. So we are seeing this from 1's point of view, and 1 prepares and accepts, and you see the meaning of life 42 as a learned value. So, and now we see meaning of life again learned for a different proposal That's because 3 reproposed the value, and you see that it reproposed 42 as its value rather than 29. Okay, so the proposal number has changed, but the value hasn't changed. So you learn only one value, though with 2 different proposals. So a question at this point is, why repropose a majority value? Why not just not propose anything? Okay, and in that previous example, that made sense. But the reason we gave was that a prepare phase can prevent some nodes from accepting the previous to be majority value. So majority value may not have percolated everywhere. And because the prepare phase was executed by the higher proposal, it locks out certain nodes from accepting the new value. Okay? And if some of the nodes in the current majority die, then some learner nodes may not get consensus value, even though majority of nodes are alive and can converge to a value. Okay? And so we want the consensus value to propagate to all acceptors for fault tolerance. That was okay. So we'll try to derive this case. So we'll create a prepare phase which prevents node 3 from accepting the previous majority value of 1's proposal accepted by 1 and 2. Okay, so we'll make sure that the prepare message goes to 3 early enough so that it will not accept the majority value of 1 that 1 and 2 have accepted. Okay, now at this point node 2 dies, then node 3 will not get the consensus value, even though majority of nodes 1 and 3 are alive and can converge to a value. 3 refuses to accept 1's message, 1's accepted value, okay, or it has refused. So, and we want consensus value to propagate to all acceptors of fault tolerance. So, constructing this case is more complicated. We have to set breakpoints in start accept phase as before. And then we also have 2 methods that are more fine-grained, and we want to make sure that node 2 does not send its response to node 3 early enough so that when it dies, that response has still not gone. We're going to make node 2 die, so we're going to delay its response to accepted response to node 3. And we are going to also have a fine-grained scheme in which the prepare from node 3 goes to itself before it goes to node 1 and 2, so that it can lock itself out from accepting node 1's value, but it can't lock 1 and 2 from doing so. Okay, so by doing appropriate resumes in these methods, we can make sure that 1 first does its prepare completely. Okay, then 3 prepares itself, but not other nodes. Okay, so that's what happens here. Then 1 does its accept to all the nodes. That accept is rejected by node 3 because it did a prepare on its node, but it is accepted by the other nodes, and the accepted response from 2 goes to node 1 and 2, but it doesn't go to node 3. Okay, so nodes 1 and 2 agree that there's a majority value, and node 3 hasn't seen that value. Okay, now 3 does its prepare 1 and 2. Okay, so now that it does that, it's ready for its accept phase. It still hasn't received 2's accepted value. At this point, we'll kill 2, so it'll never receive 2's accepted value. And then we'll do 3 accept, and if 3 accept did not accept, it did not propose the same value that 1 had proposed, we would not get convergence. So it makes sense for it to propose the majority value. Okay, so that's what we'll try to do. And 3 will not get 1's proposal, but 1 and 2 will. That's what this is saying. 2's accepted notification will not reach 3, but will reach 1 and 2. I said that earlier. Okay, and that's why 3 should repropose. Okay, so this is just reiterating what I said earlier. And we see this happening here. This is the display at node 2. Okay, so node 2 reached a consensus value of 42 and then died. Okay, so it never sent its accepted value notification to node 3. Okay. This is what happens at node 1. Okay, node 1 learns twice. Once the value associated with its own proposal, and once the value associated with 3's proposal. Okay? And in between these two values, it receives a message saying that 2 has left the session and it died. And the reason why we get 2 of these connected error messages is because in my implementation, each node connects to the other node. So each node receives a connection and initiates a connection. Okay, so that's why we have 2 responses. Okay, there are 2 duplex links between each pair of nodes. This is a minor point just to show you why we got these 2 messages. And node 3, on the other hand, learns the value only once. Okay, that's because the first value, enough acceptances never reached it because node 2 died. Okay, and we see that here, that it receives, we see why it reproposes the value 42, and that's what it learns later, because it received the value 42 from node 1 before it started the accept phase. Now, as it turns out, the other prepared notification received was from itself, which did not have 42. So it did not really receive a majority value in the prepared notifications. Before it sends the prepared acceptor, just after it sends its accept request, it receives from 2 the value 42. So had this message arrived before the accept request, it would have seen a majority value. But in this case, that didn't happen. I didn't force that to happen. But either way, we know the algorithm chooses the value with the highest proposal number, which is 1.001. So that is why it reproposes that value right here. Okay, that's what it learns. So, so that it makes sense then to repropose a value that has already been learned so that it can propagate. Sometimes you might not get a majority value, you might get a minority value, as we saw in the previous example. So then the question is, why repropose it? Well, that minority value may become a majority value, as we saw in the previous example, or it may not. Okay, so let's try to see whether that's really the case. So if it does become majority value, then prepare phase may have locked some nodes from accepting it. Okay, so that's why proposer proposes the value of the highest proposal number as its own value. Okay, and here I try to make sure that node 3 doesn't get a majority value. Okay, so node 1's minority value will become majority value. So I make sure that it will become majority value, but it's not majority when its prepare phase finishes. Okay, and so this is a sequence of steps you do to make that happen. And this sequence of steps is very similar to the next one we'll see later, so I won't go through it, especially because we've already seen a case where the value was minority when we reproposed. Okay, so in here, it'll see, I make sure that 3's prepare phase sees acceptance from 1 and rejection from 3. That happened in the previous example, but here I forced that to happen. And the value should become majority. In this example, I won't kill 2. We see this. This is what's happening at node 3. It learns the same value twice because we didn't kill 2, but this shows you why it should have reproposed a minority value, because otherwise, if it hadn't, it would learn 2 different values. Okay, so it receives one non-committal prepared notification saying I haven't accepted anything, and it receives 1 with 42, and just as in the previous case, it reproposes. Now the interesting thing here is that it learns the value 42 before it sends. As a learner, it knows that the value 42 has been accepted before, as a proposer, it sends the accept request, and so that can happen. Now here I will make sure that node 1's minority value will not become majority value. So just to show you that every minority value doesn't necessarily become a majority value. Okay, but the point is that this case is no different from node 3's point of view than the case in which it will become a majority value, and that is why node 3 has to repropose that value. Okay, so now we will construct the case in the following manner. We will again set breakpoints at the methods in the methods I've shown here, and we'll make sure that once prepare phase goes to everyone, 3's prepare phase goes to only 3, doesn't go to 1 and 2. 1 doesn't accept, and 1 sends its accept request only to itself, not to 2 and 3. So 1 will accept its value because it hasn't received a prepare request from 3. But 2 and 3 do not get the accept request, or they can't accept the value. Now 3 will prepare the rest. Okay, and at this point 3 will get a response both from 1 and 3 saying that 42 has been accepted, and that value has not reached 2, so it will not become a majority value, but it doesn't know better, so it will repropose its value in 3 accept, and once accepted 2 and 3 will go much later, and both nodes will reject that value, so 1's value will never make it as an accepted value. Okay, so 3's prepare sees acceptance from 1 and rejection from 3, just as before, but so 3 proposes 1's value, though 2 will reject 1's value as 3 does not know in what order the acceptance will reach 2. Okay, so it doesn't know whether its accept will reach 2 first or 1's accept will reach 2 first, and I made sure here that 1's accept reaches later. Okay. So we see here that the meaning of value is meaning of life value is reached only once, not twice, but that's a reproposal. Okay, so it receives from itself the fact that no value has been received, has been accepted before, but it receives from node 1 the fact that it's received 42. So same as in the previous 2 cases, but this time the value will never become a majority. Okay, finally we'll try to show that in Paxos you can have this Livelock situation where reproposals can prevent any successful acceptance. Okay, so in Paxos, if you don't get an answer soon enough, you repropose your value. The properties we'll see here are that one's first acceptance is prevented from 3's first prepare, because 3's first prepare occurs before 1's first acceptance. 3's first acceptance is prevented from 1's second prepare, which timed out. And then 1's second acceptance is prevented from 3's second prepare, and this goes on continuously. Okay. And by putting appropriate breakpoints in the methods I've shown here, start prepare, start accept, we can make this happen. So we'll make 1's first proposal prepare succeed. That's 1 superscript 1. Then 1's first proposal accept blocks so that it can time out and repropose. We'll resume 3's first prepare, and it'll succeed because it's the higher proposal number. And then we'll make its accept block so that it waits for 1's reprepare to go into the system, and 1's accept unblocks and fails and retries. Okay, so that's the timeout occurs at that point. So 1's reprepare succeeds, and then 1's reaccept blocks, waiting to timeout. At this point, we resume 3's first accept, and it fails because 1's reprepare has a higher value, and then 3's reprepare occurs, and after the retry, and it succeeds, but it blocks, waiting for node 1 to repropose. So this keeps going on and on. Okay. We see here that 1's prepare succeeds, and 1's accept unblocks and fails and retries. So it's going to retry. So you see here that it made a proposal of 42 earlier, and then it's making a proposal of 42 again later at the end. And so it receives a concurrency conflict notification. It's first accept, and that's what called, and so another concurrency conflict in the first accept, and then it remakes the proposal 42 with a new proposal number, and we see here how the proposal numbers go. The prefix is a whole number that tells you what is the highest whole number I've seen so far. That is dependent on the highest proposal number you've seen so far. So whenever you make a new proposal, the whole number part is more than what the whole number part you've seen so far. Plus you append your site ID. So this makes sure that if two proposals are made at the same time that increment the same whole number from two different sites, they have unique numbers. But this scheme also makes sure that newer proposals have higher numbers than proposals you've already seen. Okay, because you increment the whole number part, the higher order bit, when you make a new proposal. Okay, so once reprepare succeeds, it does a reprepare, and so it's going to propose a value, accept a value which will be rejected, and this shows you, if you look at it in detail, that 3's accept is going to fail because 1 prepared a new value, and then 3 reproposes, which causes 1's reaccept to fail, and so that's what's happening here. Okay, so you get a denial in the accept because 3's accept failed. Okay, that's 1.003 equals 29, that failed, and then we get an aggregate denial for 2's accept also. Okay, so everybody's getting denied, and that's because, you know, after each another prepare request superseded an accept. Okay, so the question is, what happens when you have uncontrolled execution? You know, here we controlled it, and as it turns out, you can have different values. So you made a proposal 42 here, and 29 succeeded because of the way the prepares went. That's one execution. Okay, so let's go and see what we've achieved by learning Paxos and the centralized mechanism. So both of them solve the problem of multiple users proposing at the same time, or multiple processes proposing at the same time. And the centralized is less fault tolerant, whereas Paxos is more fault tolerant, but it is more message intensive. We have 3 phases and n-square messages in the basic Paxos. So you might want to use it for changing state that doesn't change very often, like locks, or the consensus protocol you're using, or the communication protocol you're using. Okay? And for other things, you might use centralized. And for simpler cases, you might use only one proposer, so you don't even have to go to centralized. You can just go to the synchronous scheme. And for master-slave situation, you might just use asynchronous algorithm. Okay? And with this hierarchy, that the implementation we've created, we can use the most efficient scheme for our needs because we can use the functionality for superclasses. And to use that functionality, customization. And I told you there's customization, and we see a bunch of methods that I have in my implementation. And apparently customization is a big issue in industry. And in fact, I've seen talks on how we can make sure that the customization is consistent. So people have configuration files, and configuration files can have errors. So there's actually a research area that tries to make sure that customization errors occur as infrequently as, or at least the frequency is reduced. Okay.
Okay. We've been waiting for this slide. So, you know, we looked at distributed systems. We went from that to replicated systems. Okay. And the assignment I gave you was motivating replicated systems. That's why you had this replicated simulation. Okay. So one thing we want to learn is that RPC is not the highest level abstraction we need in a distributed system. We can have a replicated object abstraction. Okay. Now, the question then becomes, what kind of synchrony does this replicated object support? If we want pure replication synchrony, we need a global clock. Okay, that's one lesson we learned. Now, if we want impure synchrony, then we need propose, notion of propose, invalid state, listeners, rather than pure get and set. Okay, so we're not just getting and setting the replicated object, we're going through this process here. Okay? And the replication synchrony involves then a two-phase algorithm. And if you want to reject a proposal, you also need a two-phase algorithm. So these two things are combined together. Okay? And degree of synchrony, that means how many other nodes you consider in the synchrony and rejection can be different. And in my implementation, I've made them similar. Okay? And whenever the notion of having weaker degrees is to allow more progress at the expense of safety. Okay? So concurrent proposals was this big problem that everybody was wrestling with. A centralized coordinator solves that problem, but it can fail. If it fails, we can go and use IDs to do the switchover. Okay? But central solution can lead to inconsistency even if majority is alive. And that's where we went to three-phase Paxos. Okay? And even in three-phase Paxos, you need some centralization to make things efficient. And you need some timeouts for practical reasons. And the whole notion is that one of the interesting things in this three-phase algorithm is the notion of extracting promises, saying, hey, I'm locking you out from accepting any new value and state. Okay, guys. We all have shown great stamina. and I guess there's a third phase, accept update value. I'm just summarizing the algorithm here. Centralization to achieve consensus about update sequence.